All right, I've gone ahead and posted that as an assignment. And as before, I'll need you to upload your answers as a PDF. I made the due date tomorrow. I think I put it at 2 o'clock. Okay, so tomorrow afternoon, quiz 7 will be due. I know I've got some quiz 6 stuff to get through there, so I will grade the quiz 6 material this afternoon, and you'll get those. Okay. So let's go ahead and get on with today's lesson. Okay, so this is about section 3.4. Which is about the long division algorithm. Okay, so the long division algorithm is actually the most important algorithm for students in elementary school. Let me explain why I would make that statement. Okay, so this is needed for really understanding what an algorithm is. Okay, in the other algorithms that we've already known, we focus on the individual parts. For the multiplication algorithm, we take multiplication of multi-digit numbers and break it up into a series of multiplications of single-digit numbers, and then the algorithm is just about doing the bookkeeping. The long division algorithm kind of takes a more holistic approach. You have to look at the whole entire thing of the two numbers. Okay, so it's a little bit better example of an algorithm than the other ones. It introduces students to the idea of making successive approximations. Okay, so when we don't know what the answer is to start, each step in the process of long division is going to get us closer to the answer. And if we stop the algorithm at any point in the middle, we'll have a better approximation than the stage we had before. So this idea of successive approximations actually comes up quite a lot in mathematics, in science, in computing. Okay. In fact, calculus is really about successive approximations. Okay, so it's an important thing for students to have down because it lays the groundwork for further study in science and computing. And of course, it's important for relating fractions to decimals. Okay. So let's look at some prerequisite material. What do students have to know? Well, of course, they'll need to know their place value stuff. That is very important in the division algorithm, to keep stuff in the correct columns when we do this. And they need to have a very solid understanding of their one-digit multiplication and division facts. Okay, now this isn't something I emphasized a whole heck of a lot, but there's something called a four-fact family. Okay, something like this. Let's say this is one fact, but we automatically get another fact for free using the commutative property. So if we know 5 times 7 is 35, we also know another multiplication fact. What is it?
7 times 5 equals 35.
Right, because multiplication is commutative, we can change the order. So if you know 5 times 7 equals 35, you automatically know this. Now, this isn't necessarily part of the long division algorithm. This is the kind of thing you need to know for the long division algorithm. But this multiplication fact is equivalent to 35 divided by 7 equals 5. If we think about division as the missing factor, 35 equals blank times 7, right? What do I have to fill in there to get 35? Well, I have to fill in a 5, thinking of division as the reverse of multiplication there. And of course, we have this division fact as well. Okay, so students need to have these things down before they can start learning the long division process. Okay, and that is demonstrated, it shows up in the order of the teaching sequence for the algorithms. You start with the addition algorithm, because that's the easiest. You just need to know your addition facts within 20. And the subtraction algorithm, you need to know your addition facts within 20. Then you get your multiplication algorithm, and finally the long division algorithm coming last. Okay. Now, it's not enough to know just your four-fact families. Students need to be comfortable with the idea of quotient and remainder. This is something we talked about a little bit when we introduced division in chapter 1. Remind me of what this means. What's a remainder? Let's see, Tasha, help me out. What's a remainder?
It's like something that's left over.
Okay, right, something that's left over. So the idea is we can do division even if we're not working in those four-fact families. Okay, so we can talk about something like this. We can talk about, I don't know, instead of 35 divided by 7, we can do 38 divided by 7. 38 divided by 7 equals a quotient of 5 with a remainder of 3. Okay. For students to learn the long division algorithm, they need to transition to the long division notation. If you remember, when we introduced the operation of division, we were writing it like this. Okay, when we make the jump, we'll be doing this. And there is a fourth thing that I will mention a little bit later. Okay, there's a fourth thing. Some folks don't quite get what I mean when I say this next thing. So I'm going to hold off on saying it until I show you why we need it. All right. So there are a couple of ways to develop the algorithm. Okay, now you'll probably remember from when we introduced division, we had two ways to think about it. We had the partitive division interpretation and the measurement division interpretation. Okay, both of those are kind of important for developing the algorithm. And it's taught in 3 stages. Okay. So first stage and third stage. There is a second stage in here. Okay. So let's think out what would make sense for this. So I've got a class of students, let's say 4th grade, well, maybe 3rd grade. I forget when. I guess it depends on the school system as to when this is going to get taught. But we got students that are around 4th grade. They don't know long division yet. So what am I going to start them out with? So we've reviewed our division facts. The students know their multiplication tables, and they know their 1-digit division facts or their division facts. So how am I going to start out long division? Would this be a good problem for them to start out with? Let's do would that be a good first problem for them to do?
No,
Okay, why not?
it's too long and complicated for them.
Okay, right. It's 16 going into something. Well, we have to deal with multiples of 16. Does this make the problem easier?
A little bit.
Yeah, in fact, this goes in very easily, right? 6 into 24, we can do that. And then we've got the whole thing there. So when you start out with the long division algorithm, you do 1-digit divisors first. And then you will transition to 2-digit divisors. Okay. There is a stage 2 in here that is necessary, and The problem is a lot of people do this stage 2 part and they do it without thinking about it, okay? Because they learned the division algorithm so long ago that it's just something that goes automatically. And remember, part of this class is about being explicit about what we do automatically. Because when you're teaching somebody that doesn't know it yet, you can't just say, oh, well, you just do it. Well, how do you do it, right? That's our job as teachers, is to explain and demonstrate how and why something gets done. So let me give you a 2-digit division problem, and we'll think about the steps we could do to do this 2-digit division problem. Okay. So how about we try this? It's a long division problem. So remember, we're talking about something maybe 3rd or 4th grade level. I want you to do 56 divided into 4,832. Okay, so take 2 minutes and do the division problem. If you're having trouble getting started, I want you to think about this. And how would this problem help us get started on this problem? Okay, so let's focus on this. So what's the result here?
Can you take away a 0?
Okay, yeah, let's not take away anything. I mean, we can, but let's just look at, I mean, the point is the zeros don't actually complicate the issue. What do I really need to focus on? I need to focus on the 6 and the 48. 6 into 48, how many do I get?
8.
8, okay? So 6 into 48 goes 8 times. 60 into 480, that also goes 8 times. Okay, now the division comes out even, so the answer is just 80. Okay, now the idea here is, okay, the trouble that people have when they're starting out is, all right, 56 into 48, well, that doesn't go. 56 into 483, well, I don't know what to do. So if we think about this, we can get started. I should probably start out by putting an 8 there. Okay, now what would I do? What do I do with this 8 in the long division problem?
You would take the 8 and multiply it by 56.
Right, that's where this 480 is coming from here. It was 8 times 60. 8 times 60 is 480. Here we take 8 times 56, and that's what we would put down here. Okay, 8 times 56, something we could do mentally. We double 3 times. We got 56, you double it, 112. You double again, 224. You double a third time, 448. And then we would subtract, and then we would continue. Okay, but the idea here that I want to emphasize is if you weren't able to get started with this, it's because you've forgotten about transitioning to a problem like this. This is a process called estimation. Okay, it's absolutely critical for dealing with the division algorithm when you have 2-digit divisors. The problem with the 2-digit divisors is we don't have the multiplication table memorized for all the 2-digit numbers. We have the multiplication table memorized for single-digit numbers. Okay, but I don't know the times table for 56. However, if I transition and use this as an estimate for 56, okay, how many 60s can I get in? Well, I don't really need to worry about 483. I just need to worry about 480. I need to worry about how many 60s can I get into 480. That'll at least get me started. Okay, so flip back. When I was leaving blanks here, the 3 stages, 1-digit divisors, we also need to talk about estimation in there so that we can make the transition to 2-digit divisors. And the 4th component is estimation. Okay, so the next couple of classes will be about, well, obviously this class we're going to introduce the long division algorithm. So we'll deal with that for single-digit divisors during this class. And then we'll deal with estimation, and then we'll deal with 2-digit divisors. So the next couple classes are going to be about the long division algorithm. Okay. So let's deal with this stage 1 stuff. Single-digit divisors. Okay, so let's deal with the partitive approach here. Okay, so let's say we have this little word problem here. Miss Davis distributed 13 cookies equally among 4 children. Okay, so I'm going to write down a little skeleton for my answer. So each child got blank cookies with a total of blank distributed and blank left over. Okay. So we're distributing the cookies among 4 children. So we know this is not a multiple of 4, right? Because we know our multiples of 4. 4, 8, 12, 16. We've skipped over 13. 13 is not a multiple of 4. All right. So now we can fill this in right away here. I'm not going to do it just yet because I want to show you how the information in the long division algorithm gives us these answers. But what should I put here? Each child gets how many cookies? Got 13 cookies among 4 children.
3.
Okay, each child gets 3 cookies. So that means I would give out how many?
12.
Okay, gave out 12 cookies. Okay, let's see. Amy, how many would be left over then?
1.
1 left over. Okay, so each child got 3 cookies with a total of 12 distributed and 1 left over. Okay, now let's look at the division algorithm for this right here. Okay, so we're talking about 13 divided by 4. Okay, so 13 equals 4 times blank plus blank. Okay, the quotient and the remainder. I want to get as close as possible to 13, and then this will be my leftover. Now, would I say this? Would I say, okay, 2, right? 4 times 2 plus 6. No, sorry. 4 times 2 plus 5. Is this right?
Technically,
Yeah, I mean, technically the equation is true, but there's kind of a condition that we put on the remainder, right? If I say I divided it up and I have 5 left over, well, I could have distributed those cookies to the kids, right? So what's the maximum that I should have here? The maximum leftover when we're talking about dividing by 4.
3.
Right, the maximum I should have left over is 3. Okay, so there's a kind of a condition on the remainder. The remainder has to be less than the divisor. Okay, so 3 times 4 plus 1, 1 left over. Okay, so in other words, the quotient is 3, the remainder is 1. And the way we record this in the long division algorithm is we got the divisor out here, the dividend underneath, okay, and this number on top is telling me how many cookies each child gets. This is telling me the number distributed, and this is telling me how much is left over. Okay, so from the division algorithm, this is keeping track of how many each person gets. This is keeping track of how many we have distributed, and down here is what's left. Okay, so each child got 3 cookies for a total of 12 distributed and 1 left over. All right, now, this was a little bit easier because it just involved my single-digit multiplication facts. I just needed to know my multiples of 4, and I had to get as close as possible to 13. Okay, let's do something like this. This is also using the partitive approach. Okay, so Ann, Beth, and Carol split $8.82 equally. How much did each get? Now, in the previous example, we didn't really need the division algorithm. I mean, we answered the question just mentally. Okay, in this example, I think we really do need the division algorithm, but we can also think about why the division algorithm is working the way it does. Okay, so we're going to take 882 divided by 3. Okay, I know there's a decimal point involved, but don't get too hung up on that right now. Let's think about how we would do this in a practical sense. Let's imagine we have $8.82 and we're dividing it among 3 people. First thing I would do is I would divide up the dollars. Okay, so how many dollars would each of them get? Got 3 people, I'm dividing up $8. So right now, imagine they're dollar bills.
2.
Right, each one gets 2, okay? So each one gets 2. Now we're putting 6 down here. Okay, so $2 each. I've distributed $6. Okay. Now here's what I have to do. I have $2 left. Now the question is, well, I can't divide $2 among 3 people if I still have dollar bills. Okay. What I need to do is I need to take my $2 and turn it into 20 dimes. Okay, if I can make the change, now I can distribute that left over. Okay, in fact, what I should do is I should do not only the $2, but this 80 cents. Okay, so now I've got 28 dimes. So I'm going to think about what I should do there. So distribute the dollars, distribute the dimes. Okay, so I'm just going to write this down again. Okay, so we distributed the dollars. Each one got 2 for a total of $6 distributed. And then we turned the remaining stuff into 28 dimes. Now we're distributing those among 3 people. So we're focusing here on the dimes. So I got 28 dimes. I'm distributing them among 3 people. How many dimes does each person get? Let's see, Aspen, how many dimes? I got 28 dimes. I'm giving them to 3 people.
Nine.
Right, 9 dimes. Each person gets 9 dimes. Now, how many dimes would we be giving out then? Are we giving out all 28?
Just 27.
Right, we've given out 27 dimes, which means we have one left over. Okay. So now what do I do at this stage? Do I just say, oh, well, we're done? You can't break up one dime among three people. What could I do? Is there a smaller denomination that might help out?
Distribute pennies.
Right, work on the pennies. Okay, so change that. I guess we've got 12 cents instead of one dime, 2 pennies. Let's do 12 pennies. Okay, so we convert that to pennies, and then each person would get 4 pennies. And then we've distributed everything. So each person would get $2, 9 dimes, 4 pennies, 294. Okay, so that's essentially what is happening in this long division algorithm. You're making change at every stage. And this is a good example for showing the role of that place value property, the dollars, the dimes, the pennies, okay, the hundreds, the tens, the ones. Notice that each step is the same. At each stage of the algorithm, we distribute as much as we can, and then we take whatever's left over and we make change to the next denomination down. We get rid of as many dollars as we can. Now we have got $2 left. We can't distribute that among 3 people. So we make change. Instead of treating those as 2 hundreds, we treat them as 20 tens. And then we keep on going that way. And each step gives you a better approximation than you had on the previous step. Okay, notice here on the first step, okay, $2 each. That's an okay approximation of what everybody's going to end up with. If you're talking about just whole dollars, they each did end up with 2 whole dollars. At the next stage, before we did the pennies, $2.90, a better approximation to the answer. And then finally, we got the pennies. Each person got 4 pennies. Okay. Okay, so let's talk about how we could interpret this in the measurement division sense. Okay, so the idea that we're thinking about is how many 7s are there in this big number? Okay, you could also think of this as repeated subtraction. I got 1984. How many times could I take away 7 from this? Okay, now, if I were to just start taking away 7s, the bookkeeping would become overwhelming. Obviously, there are a lot of 7s in here. Okay, so here's a little strategy that is helpful. Don't start taking away 7s. start taking away larger multiples of 7. Okay. We could try taking away 7D. And remember, I'm dealing with multiples of 10 because of our place value system. Could try taking away 7Ds, and that would be nice. But I could do something even bigger. I could do 700s. Could I do 7,000s?
No.
Right, this is not enough. I can't take away 7,000 from 1,984. Right, but I can take away 700s. In fact, I could do quite a few of those, I think. Let me draw it out on a number line here. If I was taking away 700s, well, my first 700 would get me to 700. If I did 2 of them, that would get me to 1,400. What if I did another one? Could I do another one? What would the next 700 take me to? Think about taking jumps of 700. 700, 1,400. What would the next one be?
2,100.
Right, 2,100. So can I do that? Can I go to there if I'm talking about taking away 700s from this?
No.
No, that's too far, right? My number is 1984, and it's right here. Okay, so now what I need to do is I need to make up this difference. Okay, jumps of 700 can get me kind of close. I can do jumps of 700 and get to here. Now I need to make up that difference. Okay, and that difference is 584. Now let me start and put down my division algorithm here. 1984. Okay, now think about how we start the division algorithm. How would you start this? You think about 7 going into 1. It doesn't go at all. What do you do now?
7 into 19.
Right, you do 7 into 19. And how many 7s can you get in there?
2.
2, okay? But let's think about place value here. This is not 19, this is the hundreds place. This is 1900. Okay, so we can get 2 jumps in the hundreds place, 2 jumps of 700. And then we would do this, right? We would write down the 14. So we get 584, right? Notice that's the difference that I have to make up. Okay, so what I want to do now is I want to do jumps. Now we're in the tens place. I want to do jumps of 70 until I get as close as possible to 584. Okay, and I'm thinking about jumps of 70. My next one would, of course, be 140. Okay. So how many jumps? What's the closest multiple of 70 that I can get to this? If you need to, just keep on counting up.
$560.
Okay, 560. Now, remember, you don't need to know your multiplication table for 70 to get multiples of 70. You just need to know your multiplication tables for 7, right? So you got 7, 14, 21, 28, 35, 42, 49, 56. The next one is 63, so that's too big because that'd be 630. So we can keep on doing this until we get to 560. Okay, and if we look at the next stage in our division algorithm, here's what we would have, right? 1, 9, 8, 4. 2 times 7 is 14. Give me a 5. We're looking at 58. Okay, so 580, the 4 is kind of something that comes down there. right? We just do that, I guess, if we want to do a full subtraction. Okay, now we're in the tens place, so we're talking about 70. That was 8 times 7. Okay, 8 times 7, 560. Now, the difference that we need to make up is 24. Okay, so now I'm talking about steps of 7, because I'm in the ones place. Okay, so how many 7s can go into 24?
Three.
Right, 3 7s, because that gets us to 21. And I would have 3 left over. Okay? So, the interpretation of measurement division is you imagine that you have these, you're making these jumps. Okay? And each stage you're making smaller jumps because you're refining your approximation. If you're allowed to use jumps of 700, well, the closest you can get is jumps of 2. Or sorry, 2 jumps of 700, getting to 1400. You can't take another jump of 700 because then you go over the target. Now your difference, work on the difference now. Use smaller jumps. Remember, we're talking about successive approximations. So at the first stage, we're getting in the biggest jumps we can possibly make that are multiples of 7. Okay, and the biggest jumps we can possibly make are multiples of 700. So 700, 1400, can't do any more. Now we're working on 584. Do jumps of 70, the biggest possible multiple of 7 that you can get in there. You can get in 8 jumps, getting you to 560. Now you can't do another jump of 70 because you exceed that target. Now you got 24. Okay, it's a finer approximation. Okay, so we got the partitive division algorithm, or the partitive interpretation, the measurement interpretation. I do want to show you one example using the chip model. Okay. Let me try this. I want to try let me make it kind of small here. I'll do 35 divided by 2 in the chip model. Okay, so how do I start out with the chip model? Just anything.
Make trays.
Okay, we make trays. Okay, so we want the tens tray and the hundreds tray. Well, sorry, went the wrong way. The tens tray and the ones tray. Okay, so 1, 2, 3, 1, 2, 3, 4, 5. All right. Now, for doing this division algorithm, for modeling division, you need to start here. Oh, okay. I'm going to change up the problem slightly. Instead of 35 divided by 2, I want to do 75 divided by 2. The answer would have been it would have been too specialized. So you might not have seen what was going on if I just had 3 there. Okay. Okay, so I've got 7 chips here. I want to make 2 equal groups because I'm dividing by 2. All right, so how big are my groups going to be? Let's see, Cynthia, how big are my groups going to be? I got 7 chips. I want 2 equal groups.
Mm, 37.
Don't try to go to the answer. Just focus on the tens tray for right now. Okay, so I got 7 chips in the tens tray. I want to break them up into 2 equal groups. How big should my groups be? And what do I have left over? I'm going to have 2 groups, and I'm going to have some left over. I got 7 things.
So 2 groups of 3.
Okay, 2 groups of 3. So 1, 2, 3, 1, 2, 3. Now I have this 1 left over. Okay. What I'm going to do is I'm going to make some change, just like we did with that dividing up the dollars problem. So I divide up the tens chips into 2 equal groups. I got this 1 left over, I make change. Now I had 5. So that's going away. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this comes from making change. Okay, now I've got this. So let me try to get both pictures in the on the screen here. Now I've taken the tens tray and I've divided it up into 2 groups of 3. Now in the ones tray, now I've got 15. Okay, so I want to make 2 equal groups. Let me see, Emily King, help me out here. I got 15 chips. I want to make 2 equal groups. How many in each group? And what's the leftover?
7 in each group and 1 left
Okay,
over.
7 in each group, 1 left over. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1 left over. That's my remainder. Okay, so remember, the model should show us the answer. Okay, there's your answer. Okay, you're making 2 equal groups. Well, the groups are 3, 7. 37, remainder 1. Okay, so that's how the chip model works for division. Remember, you got to start on the other side. Okay, in the other algorithms, we always started in the ones place, and then we were regrouping. Division, you got to do it the opposite. Okay, it's one of the more complicated than the other ones. Okay, so read section 3.4 in elementary math for teachers. So I know we're a little bit over time. Let's just kind of polish it off here. So section 3.4, which is pages 71 through 76. Okay, 71 through 76. And I want you to work on problems 2, 4, and 7 on page 76. Problems 2, 4, and 7. Okay, I don't know if we'll be in class in person on Friday. We'll have to wait and see. Okay.